Have you ever just stared at a line of code and wondered how a computer turns that simple text into, well, into an action? It really feels like magic sometimes, doesn't it? But it's not. It's architecture. Today, we're going to pull back the curtain and look at the hidden blueprint that every single programming language follows. This is the structure that lets us talk to machines. So let's get into it. Okay, look at this. A equals B plus C. Simple, right? We see it and we get it instantly. But for a computer, this is just a string of characters. How in the world does it know that A is a place to store something, that equals means put this over there, and that plus means add these two things? That's the big question we're going to break down today. So here's our game plan. We'll start with this whole idea of a blueprint for code. Then we're going to peel back the 4 essential layers that make up a language. We'll dig into syntax, the grammar, and then get into the really juicy part, semantics, which is all about the meaning. And to wrap it all up, we'll see what this blueprint tells us when our perfectly good code suddenly goes bad. Right, so let's get this idea in our heads. Programming is not some mystical art, it's architecture. Think about a detailed building blueprint. Every single part, from a tiny screw to a massive support beam, has a specific place and a specific purpose. It's all governed by a very strict set of rules. Code is exactly the same. And this blueprint is what makes everything work so reliably. It's like a contract between you and the computer. If you follow the rules, if you follow the structure, you have a guarantee that your instructions will be understood and carried out correctly. Every single time. It doesn't matter what machine you're on as long as it understands that same blueprint. To really get what's going on, we need to look at the different layers of this blueprint. You can think of any program as having 4 distinct layers of structure, and each one builds on top of the one before it. Let's start peeling them back. We start at the very bottom with the lexical layer. This is just the basic vocabulary, the words. Next up is the syntactic layer. That's the grammar that tells us how to arrange those words. After that, we get into the meaning, or semantics. And you'll see this actually has 2 parts, a contextual check before the program even runs, and then the final semantic meaning, which is what the code actually does at runtime. So this first layer, the lexical structure, is pretty much the language's dictionary. It just defines what counts as a valid word. It's what tells the computer, hey, if is a special keyword, my score is a name some programmer made up, and plus is an operator. It's the absolute ground floor of understanding. Okay, so once we have all our approved words from the dictionary, the syntactic layer gives us the grammar rules. It tells us how to combine those words into valid sentences, or, in our world, valid statements. And this is all about the structure, not the meaning. And this is a really, really important distinction to make. Syntax is only asking one question. Is this sentence put together correctly according to the rules? It's all about the form. Semantics, which we're about to get to, asks a totally different question. Okay, it's a valid sentence, but does it actually make any sense? Now, these grammar rules aren't just some loosey-goosey guidelines. Oh no, they are defined with mathematical precision. To make sure there's zero ambiguity, language designers use these special notations. You can think of them as a language for describing languages, to formally lay out the entire syntax. And here's a classic example of one of those formal methods. This little snippet is a rule written in what's called Backus-Naur form, or BNF. And all it's saying is an assignment statement is defined as a variable, followed by an equal sign, followed by an expression. See? It's a super precise, totally unambiguous blueprint for just one tiny piece of code. All right, so we've followed the blueprint. Our code is grammatically perfect. Awesome. But does it mean anything? Does it make sense? This is where semantics comes in. Now we move past just the structure and we get into the meaning and the actual intent of our program. The first part of semantics is what's called contextual structure, or static semantics. You can think of this as a check that happens before you even run the program. A piece of code can be syntactically perfect, but still be complete nonsense in context. For example, trying to add the number 5 to the word hello. The grammar is fine, but the context, the types, is all wrong. The compiler is going to catch that and say, nope, not happening. And that brings us to the final layer, dynamic semantics. This is it. This is the whole point. This is the ultimate meaning of your code, what it actually does when it's up and running. It's the logic, the behavior, the final result. This is where the rubber meets the road. Now, trying to formally define this execution behavior, well,
it gets incredibly complicated really fast. It's a whole field in computer science with different ways of thinking about it, like operational or axiomatic semantics. We're not going to dive in deep here, but just know that precisely defining what code does is a fascinating and really tough problem.
So you might be thinking, why does all this layering matter? Well, here's the payoff. When you understand these layers, you can understand your mistakes so much better. See, bugs aren't just random. They happen at very specific layers in this blueprint. Let's look at a few examples. Okay, check this out. At the lexical layer, you could have an error like int 2x. That's basically a typo. 2x isn't a valid word for a variable. A syntactic error is a grammar mistake, like forgetting a semicolon. You broke the rules of the language's structure. Then there's the contextual error. Like we said, trying to add a number to a string. Looks fine, but the types don't match. And finally, a semantic error. This is a logic bomb. Dividing by 0 is perfectly valid, syntactically and contextually. But when you run it, boom, the logic is flawed. And that is why all of this is so important. This isn't just abstract theory. The next time you get an error message from your compiler, knowing if it's a syntax error or a type error tells you exactly where to start looking. It turns debugging from a wild goose chase into a systematic search. It's a way of thinking that makes you a much, much better problem solver. So when you really get this fundamental architecture of code, you realize you're not just typing instructions anymore. You're designing elegant structures. You now hold the blueprint that powers pretty much everything in our modern world. So with that kind of power, the only question left is, what are you going to build with it?